Hi, everybody. I'm Matthew Frost. I'm a PhD student at the University of Western Australia. As you can see behind me, I use high-resolution simulations of disk galaxies to understand the processes that lead to bar formation. Now, I've been keeping a tally, and so far, I've only heard 3 mentions of bars at this conference. And that's unfortunate because we know at redshift 0, over half of all disk galaxies host bars. And that means if we want to understand galaxy formation and evolution, we need to understand bar formation and evolution. If you're an observer, bars should matter to you, right? They mess with your bulge disk decompositions, they change your star formation histories, and they're going to disrupt your kinematics. If you're a simulator, it's the same story. We also struggle to reproduce the observed bar population at redshift 0. If you want to know more about what it takes to form barred galaxies, if you want to know how we can use bars as a tracer for dark matter across all redshifts, and if you want to know how bars pertain to your work, come talk to me. Thank you.
The next one will be Esteban.
Hello, everyone. I'm Esteban, last year PhD student, and in my last project, I have been working using the Eagle cosmological simulation to study the effect of mergers in the stellar and gas kinematics. So in order to quantify the kinematics, what we are using here is the kappa-co parameter, which is the fraction of kinetic energy invested in co-rotation. So the larger this parameter, the more rotation is supported / disky your structure is. So here I'm showing the evolution for 2 different samples. This is the median evolution for galaxies in a merger sample, which is the thick lines, and for a control sample, which is galaxies that didn't have any merger in this redshift span. This is normalized. This is plotted as a function of a time normalized with the time of the merger, where zeros where the merger happened. So here you can see that, as expected, the mergers do affect the kinematics of your stellar and cold gas component. But in the case of the gas, something interesting here is that if you look at 1 gigayear after the merger happened, you can see that the kinematics doesn't change. It's not very different with respect to a galaxy that didn't have a merger, which is very interesting. So I haven't mentioned anything about mass ratios, gas fractions, but what can I say is that they impact a lot in the evolution of this on this parameter. So if you have any questions about that, just come ask me. Thank you.
Okay, Marcy.
Yep. Hi, my name is Marcy Mun. I'm a PhD student at ANU. Today, I'd like to highlight some of our findings on what governs the star formation activity of MACPI galaxies placed in context of galaxies in the local universe as probed by the MANGA survey. Here we're showing 2 plots of the radial variation in the local star formation activity of galaxies as a function of different star forming states, as defined in the top right panel over there. So overall, we are seeing similar trends in the spatial variation of star formation activity, although we do see a notable difference between the main sequence blue and green valley green, as indicated by the black vertical bars at these 2 epochs, which may indicate differences in quenching timescales. Furthermore, with MACPI galaxies, we are able to probe further out to the outskirts, such that we are able to capture decline in star formation activity in the green profile, which hints at signs of outside-in quenching due to environmental effects. And now we plan to connect these results to a suite of simulations using Muse-matched mock data queues, courtesy of Kate Harborn. So please stay tuned for that, and also a forthcoming paper on these observation results. Thank you.
Okay, Lucia.
Hi all, my name is Lucia. I'm a second-year PhD student at ICRA UWA. So my work is observationally focused on studying the intra-halo light or intra-cluster light on gamma galaxy groups and cluster of galaxies. In my work, what I do is, as this is a very faint stellar component, we need deep observation. So I use HSC to ultra deep observations from HSC. And we were able to measure a surface brightness profile that goes beyond the bigger radius of a particular gamma galaxy group. And we also obtained that the IHL fraction goes beyond 7 and 16% for this particular system. So if you want to know more about this, please talk to me. Thank you.
Nicolo.
Hi, I'm Nico. I'm a second-year PhD student at UniMelb. What I did is I used the multi-depth field, like the latest HST legacy field, and I've done clustering measurement. Did I succeed? Yes, I did. at high redshift, so it's even like posh or like bougie to say. And I was able to measure the angular correlation function at high redshift, and also to outline the evolution of galaxy bias with redshift in relation to the Austin Elo mass function. And I hope to do that with JWST data coming out this month, maybe with JADES or so. I'm not sure. Thank you so much.
Okay, Eric.
Hi, everyone. I'm Eric Muller. I'm an honors student at the ANU, and I work with data from SAMI and MAGPIE to look at dust in galaxies. So the reason we want to look at the dust in galaxies is because the dust will redden the galaxy's SED, as I'm showing in the top right plot. So this can cause degeneracies when you have galaxies that are intrinsically red or galaxies that are just red due to a high dust content. So understanding this better and the trends of dust will hopefully allow for a low observational cost correction to be made to galaxies that we look at in the future. So I'm using SAMI and MAGPIE data because they not only probe different redshift ranges, but they also allow for a resolved look at the dust in galaxies, because previously a lot of stuff has been done with integrated stuff instead of resolved things. So these plots are part of my current work where I've shown the content, the dust content against galaxy properties. Here I'm just showing 3 of them: metallicity, star formation rate, and stellar mass. There will be a lot more added to this. This is still a work in progress. And another important thing will be comparing these trends to trends from integrated surveys that have been done in the past. So if you have any questions, suggestions, science applications, please feel free, come and have a chat or come email me. Thank you very much.
Once.
Hi, everyone. My name is Evans, and the second year PhD student at UNS of Canberra. I work with Ashley, Stan Buddha, and then Evo. So basically, we are looking at nucleosynthesis within stars, and we are using Gala and Omega plus. Why are stars important? Or the first diagram on the top left corner shows basically the periodic table of elements which are present all around us, from the water we drink in the form of hydrogen and oxygen to the calcium in our bones. So they're pretty much all over around us. And also very important is the fact that they're also very sort of basic constituent of the building block of the universe. So why should we care about these stars? We should care about them because they are basically all around us and they are all over us. And we do this by studying them using GALA, which is the galactic archaeology, using the Hermes spectrograph. And they're important because when we measure the various synthesis, we get the spectra from them, and spectra give us unique features of the various elements that we look at. And from the results we've looked at, the sodium actually shows an octane, and these elements are produced by the various processes and various element or synthesis. And sodium actually is produced by corpuscular supernovae, but the results indicates otherwise. So basically, we are using what they call the Omega plus one zone model for simulation of galaxies to investigate this by trying different type of synthesis processes such as Japanese supernovae, AGB, and other sort of stuff. So if you want to talk to us about this work, I'm happy to speak to you, and thanks for your time. Amen.
Lydia.
Hi, my name is Lydia. I study at Swinburne. I think you've been teased for more than a minute already, so I'll keep it short. But just a quick reminder, ultra-diffuse galaxy is really big in size, small in stellar mass. Unfortunately, it doesn't cancel out and make them normal. The one I'm looking at is interesting because just from imaging, it has over 50 candidates for globular clusters, which is more than you'd expect. And imaging comes with an unfortunate lack of redshifts. So I have spectroscopic data for 28 of those clusters. They seem to be fairly close together. That's also fortunately close to the galaxy velocity. So I consider them confirmed for this talk. And the implication that has is because more globular cluster means more dark matter through that linear relation. But this seems to have an overly massive dark matter halo. And for further spectroscopic kinematic analysis, you'll have to stay tuned for future talk. Thank you.
Armin.
Hi, I'm Aman. I'm a PhD student at UNSW, and I like to study tidal features, which are these really gorgeous warped and extended distributions of stars around galaxies that are an indicator of recent merger activity. With the upcoming Rubin Observatory's Legacy Survey of Space and Time, we're going to have an unprecedentedly large sample of such objects to study. which will help us test some of the more sensitive predictions of cosmological simulations with regards to mergers. And so what I'm trying to do is shove this beautiful Rubin observatory into some of our best cosmological simulations and look at what we're seeing with respect to their tidal features. And so here are some preliminary results of my visual classification. Alice, please help me. And what we're seeing is some of our bigger simulations, Eagle and TNG, are agreeing really well. There are some differences with New Horizon Magneticum. If you'd like to ask me about this or see some of the further statistical analysis, please come talk to me. Thank you.
Okay, Simon.
Hi, I'm Simon Ho from ANU. So my paper on FRB was recently accepted by APJ. Fast radio bursts, aka FRB, they are like random Wi-Fi signal from deep universe, but they are also excellent cosmological probe. So in this paper, we estimate the number of the burst of future Taiwanese telescope, which is the Christmas tree down there. We can detect about 24 lens FRBs in the future per year. With this number, we can have a better constraint on dark matter lengths by primordial black holes down to 10 to the -4. And we also cover 10 to the 100 solar mass region that no one did before. So in the future, we can extend this work with telescope like ASCAP, or also we can do some follow-up analysis with like Wallaby or Magpie to study their host properties and environments. So if you're interested, please talk to me and scan the QR code to see my paper. Thank you.
Kirsten.
I'm Kirsten Banks, PhD student at UNSW, and I want to help galactic archaeologists map the Milky Way galaxy. Now, red clump stars are a really great way to do this because they're standard candles. Like the mean intrinsic dispersion of these is around 0.2 in all color bands, which is great, fantastic. However, they look a lot like red giant branch stars with similar surface features such as temperature and colors. And red giant branch stars, they're not standard candles, they are imposters. Good news, astroseismology, the study of star quakes, does a really good job at separating these two stars. Bad news is it takes a long time to get enough data to actually separate these things. Like I'm talking months to years. The solution? This astroseismic information is actually imprinted in the spectra of these stars to separate them. And my paper that discusses this result has just been accepted to MRAD, so go check it out. Now, there are clear differences in the flux between the red-lined red clump and black-lined red giant branch stars, and particular features that are dominated by CN, CO, and CH features. Find out more in my latest paper, and if you want to find out how you too can predict classifications by data-driven methods, come to me.
All right, so today we're going to talk about the S-process abundances of the Milky Way with GLA, and in particular, where the S-process abundances like yttrium and barium are coming from. So the S-process abundances are made in AGB stars, but that's a pretty broad statement, okay? Because AGB stars span a large range of mass. They can be anything from 1 solar mass all the way up to 7 or 8. So what we want to try and do is investigate if more massive AGB stars might produce different proportions of S-process abundances than lower mass AGB stars. And so this is where the thick disk or high alpha stellar populations are useful, which I've highlighted in the black boxes here. And so for these stars, they're the oldest in the Milky Way, and the FEH is directly related to the age of the star and acts like a clock. So the y-axis for each plot that I'm showing here is the barium, is the tidal basically. So this is barium, yttrium, and barium to yttrium. And so what you see is that for the oldest thick disk stars, only massive things are contributing, only massive stars can have contributed at this time to produce S-process elements. And you can see the barium is dropping very rapidly, and somewhere around FEH of -0.4, it flattens out. And at this metallicity is when lower mass stars, 2 to 3 solar mass stars, can start to contribute. But you can see yttrium is more or less flat for the whole time. So what this is telling us is that massive AGB stars are producing a lot of yttrium, but not much barium, whereas the lower mass AGB stars are producing about equal amounts of both. And that's it.